Welcome back to another video. The very first rule of derivatives that is typically taught is the power rule. The derivative of x to the n, you bring the coefficient down and then subtract 1 from the exponent. This is an iconic rule, and I'm not gonna lie, this rule was the foundation of so much stuff that I have done in calculus, and I only learned exactly how to prove it very recently. It's eluded me. But today I am here to show you the reason why this is true. Okay, maybe I kind of lied. I'm not actually going to be talking about it just yet, because in order to talk about it, we need to talk about a couple of special things. First of all is E, a very special number named after Leonard Euler, a famous mathematician. It is an incredibly important constant, and also the natural log function. This, again, is incredibly important, and it's defined as the logarithm base E. Since we're talking about calculus, I'm assuming that you have already worked with things like logarithms, and you've probably already seen E before. So hopefully this is nothing exceptionally new to you, but I'll run through a quick definition of exactly what E is right now. The most famous and most common way of thinking about what E is in terms of compounded interest. What the heck does that mean? Here we have an example of 1 plus 1/2 to the second power. This is essentially saying you put in $1 into the bank or whatever, and it's compounded with a rate of 50%, or 1/2. So you get 1, then 1.5, then 2.25, because it happens twice. Say it happens every 6 months for twice in a year. Now here, imagine the interest rate is 1/12, but it happens every month. So it happens 12 times throughout the year. I won't go into what the exact number on that is, but it's 1 plus 1/12 to the 12th. Okay, but now what if it's daily? And you get the point. The idea of E is to take that compounded interest and make it continuous. What that looks like is, instead of 1/12 or 1/365, we have the limit as n approaches infinity, right? The number just gets bigger, of 1 plus 1/n to the power of n. And this converges to E. So E is a very special number that has to do with the idea of continuous interest. Now, E is incredibly important in calculus because, and you've probably seen this before, the derivative of e to the x is equal to e to the x. And the exact reason why is absolutely beautiful, but I won't be getting into all of that right now. But we are going to talk about why this is true in terms of the difference quotient. I know you love to see this thing. As the limit h approaches 0 of e to the x plus h minus e to the x over h. This will describe the derivative of e to the x. Now, let's do some algebra. Exponent rules say that this is e to the x times e to the h, which means we can factor out an e to the x here and an e to the x here. And since that doesn't have any h's in it, we can actually take it outside of the limit. So what we get is e to the x times the limit as h approaches 0 of the e to the x is factored out, so it's just e to the h, and then e to the x is factored out, so it's just minus 1 over h. Now looking at this, we still have a problem of 0 over 0, right? E to the h, when h is 0, anything to the 0 is 1, so it's 1 minus 1 is 0 on the top, and then of course 0 on the bottom. So we can't simplify this just yet. However, there's a very neat trick we can do here. What we're going to do is we're going to use our definition of E that we had earlier, where E is equal to this limit of 1 plus 1 over n to the n, and then since we're raising it to the h power, we just multiply the power by h on this side as well. Now, I love this trick. Instead of taking the limit as n approaches infinity, we're going to see that this limit, 1 over n, goes to 0. So the limit as h approaches 0 of 1 plus h. We substitute in h instead of 1 over n, and we change the limit. And the same thing for the exponent. Since it goes to infinity for just n, if we change it to 1 over h, when h goes to 0, it still goes to infinity. But notice what we have. We have 1 over h times h. And so this just becomes 1, and we get this e to the h as the limit as h approaches 0, so it's still the same limit, so that's all good, of 1 plus h to the 1, which is just 1 plus h. So this one and this one will cancel, right? Minus 1, 1, and we're left with just h. So it's e to the x limit as h approaches 0 of h over h, but of course, all of this is just 1, and so the derivative of e to the x is equal to just e to the x again. Now we're going to do something similar to prove the derivative of the natural log of x. And remember that natural log of x is equal to log base e of x. That's the definition of natural log. So we begin with natural log of x plus h minus, you get it, it's the difference quotient, right? Next, we're going to simplify. I'm assuming you're familiar with log rules. So we see that this natural log and this natural log must have the same base. So when you subtract, you can divide their inputs. And then some simple algebra shows that this is 1 and this is just h over x. And so it's ln 1 plus h over x. All right, I don't want to have to keep rewriting the limit over and over, so just keeping it in the corner to remind us this is all the limit as h approaches 0. Now, what we do next is we bring up this over h to the front as a 1 over h. Now, again, as a log rule, if you have a constant multiplying by the log, you can put the constant as a power of the input. That's just a log rule. We're not going to go over the proof of why that is in this case or this series at all. But maybe I'll talk about it in a future video much down the line. So we see that this is very similar to our definition of e, right? However, we have an h over x here and we have a 1 over h here. It's not quite right. It'd be super nice if we could just multiply this by x so that we could have that 1 plus h and then to the power of 1 over h that we had earlier for the definition of e. And in fact, we can do this. If you multiply the front by x over x, remember this is just 1, obviously, so we're not changing anything, we can take this x and put it to this exponent, right? Because when you raise the exponent to another exponent by the log rule, you multiply them together. 1 over h times x is x over h. So what we're left with is 1 over x times the natural log of 1 plus 1 over x, h over x, to the x over h. Now, since it's the limit as h approaches 0, this is actually the exact definition for e that we had before. Just imagine u equals h over x, and so it's 1 plus u to the 1 over u. And since h is approaching 0, u must also be approaching 0. So this is equal to e, which means that this whole thing is equal to e. And since it's log base e of e, when you have log base of the base, it must be 1. So this cancels out to just be 1, and we're left with 1 over x, which means the derivative of the natural log of x is equal to 1 over x. Now, in the next video, we're going to use the results that we just found there to prove the product rule. I know this seems a little roundabout, and how the heck could this possibly relate? But trust me, the payoff will be worth it in the next video. But as always, thank you guys so much for watching this, and I hope you found it interesting.